was not only the class number, which annihilates the class group, of course, but also slightly more sophisticated elements, like when you have a abelian extension, or more generally a Galois extension, you have the Stickover element. And this thing is used, for instance, in Wiefer's, in the proof of Wiefer's criterion for Fermat's last theorem. But it's also used by Mihailescu to get this double Wiefer's condition, p to the q minus 1 congruent to 1 mod q squared, and q congruent to p minus 1 mod q squared. You see there are no class number conditions. It's really neat. And only 7 double Wiefer's pairs are known. Some of them are pretty huge. But on probabilistic ground, we expect to have infinitely many. A more sophisticated annihilator of CL of K, well, what I'm saying is slightly false, but bear with me, is given by Fain's theorem. And this is used in a fundamental way by Mihailescu for the complete proof of Nepelan, but also in different contexts, such as in the Birch's stringent diagonal conjecture. So it's really a very important theorem. René Schoof informed me that, in fact, you don't need at all the full power of Fain's theorem in the proof of Mihailescu. You need only a part which can be proved rather easily using Hilbert-90. Is that what you said, René? I don't know if you're there. Anyway. So let's come back to an equation which I mentioned when I was talking about local methods. The equation y squared equals x cubed plus t. That's another illustration of factoring in number fields. I remind you that we're talking about the very classical methods of factoring in number fields. So we've already solved this equation globally using in special cases. If you want to do this more generally, the natural number fields which you can try factoring it are q of square root of t, if you put the t on the left, or q of cube root of t, or minus t, it's the same thing, if you just factor x cubed plus t. But the problem when you work with Diophantine equation mostly come not so much with the class group, but with the units. So you really want to try and avoid, if possible, units. Now, a cubic number field always has non-trivial, non-torsion units, so we don't really want to factor in q of cube root of t. And also, in the quadratic case, if you want q of square root of t, when t is positive, this also has infinitely many units. So real quadratic fields are considerably more nasty than imaginary quadratic fields, so we really would prefer t to be negative. So let's assume this for simplicity, that t is negative. So then you just factor y minus square root t times y plus square root t equal x cubed. So it's an imaginary quadratic field. Once again, if the factors are not coprime, then coprime at least as ideals, then the solution is much more messy. So let's assume that we want them to be coprime. And for this, it's very easy to see that if you simply assume that t is square free and t not congruent to 1 mod 8, essential condition, then they will be coprime. Now, if t is not square free, it's not really that bad. You can still handle the equation by reducing, in fact, to the square free case. On the other hand, the restriction t not congruent to 1 mod 8 is really essential. Otherwise, you're really in trouble. Then you deduce that the ideal y minus square root tzk is the cube of an ideal, and you're back to the FLT situation, in the sense that if the class number is not divisible by 3, then 3 is coprime to h of k, and you do exactly the same as before, and you obtain a condition which is only on elements and not on ideals. So everything works. And then you can give an absolutely complete solution under, of course, all these restrictions. So the restriction t negative, t not congruent to 1 mod 8, t square free, and 3 does not divide the class number. That's many restrictions, but not that many. So you can give an absolutely complete solution to this equation under these restrictions for variable t. I mean, you don't have to fix t. On the other hand, if you have a fixed t, which does not satisfy all these conditions, then you can solve the equation, but it's considerably more difficult. And essentially, what you have to do is to solve a system, not a system, a series of two-way equations. I'm not going to say how you do this. It's mostly algorithmic now, but it can be quite hard to do. But you can do it for each specific t. So two-way equations are really a very nice application of Baker methods. And if you don't know how to solve these things, I advise you to read books which explain how to do this. Well, my book, of course, does, but that one has not appeared yet. On the other hand, there is a very nice blue book in the Cambridge, or is it called Cambridge Text in Mathematics? I don't exactly know the name of the series, by Nigel Smart, called The Explicit Resolution of Diophantine Equations, the title, something like that, which explains in great detail how you solve algorithmically two-way equations and other, of course, Diophantine equations. So now I would like to start on one of my favorite topics. It's really an amusing topic for those of you who've never met it. Many people here are much more expert on this subject than I am, but that's not the point. It's really a very amusing equation. I could have devoted an entire course entirely to this equation, but then the course would have had a very different flavor because I would have had to speak about quite a number of other, much more sophisticated things of which I'm really much less competent to speak about. I would have had to speak about Falting's theorem. I would have had to speak about the Ribet-Wiles method of solving using modular methods to solve Diophantine equations, Ribet's level lowering theorem on modular forms and so on. So it would have been much, much more highbrow, and that's not my style. So I decided just to show you this in an elementary way, but it's really a fascinating subject. You can really spend a whole year giving a seminar on this. It's so interesting. I mean, there's so many different aspects to this equation. So I'm just in 3 or 4 slides, I don't remember how many I wrote, just going to give you the main, some of the amusing facts. So first of all, this equation, you see, you assume that P, Q, and R are integers, greater or equal to 2. This equation is not homogeneous. And of course, this is the main thing which differentiates it from the ordinary Fermat equation. For instance, if you want to apply Falting's theorem and say, well, under certain conditions, this equation has only a finite number of solutions, well, Falting's theorem basically tells you, in fact, it tells you more, but basically it tells you that a curve of genus G greater or equal to 2 has only finitely many solutions. Unfortunately, there is no curve here. It's some messy stuff. I mean, it's not homogeneous. So you need some nice trickery, which was done by Darmon and Grenville, who really proved that. But I'll come back to, well, in fact, it's at the end of the slide. So anyway, so since it's not homogeneous, the thing that you say at the beginning of the Fermat equation, you can always assume x, y, z pairwise coprime. Well, this is not automatic. And in fact, if you don't add this condition, this equation becomes rather ridiculous. For instance, just for fun, I computed in less than a thousandth of a second this solution to the 357 equation. See, you have this cube plus this to the 5th equal this to the 7th. And if you ask Bjorn, present here, in the first row, what he thinks about the 357 equation, I think he would tell you that it's absolutely hopeless for the moment to be able to solve this equation when you assume x, y, z pairwise coprime. On the other hand, finding a solution is, if you don't assume that, it's completely trivial. Okay, so we add this condition. So it's an excellent exercise. Given P, Q, and R, well, I don't know how to do this really in complete generality, but let's assume P, Q, and R, for instance, 2 of them are coprime. Then it's very easy to construct this kind of stupid solutions. You can't call them trivial solutions. They're not trivial, but they're stupid. So we set chi equal 1 over P plus 1 over Q plus 1 over R minus 1. It's a very interesting quantity, this chi. First of all, if you look at it purely from a heuristic point of view, you count the number of integers which are p powers up to some big bound. Well, that's a bound to the 1 over p. and then which are q powers, that's the bound to the 1 over q, and so on. So the number of expressions of the form x to the p plus y to the q minus z to the r is essentially x to the 1 over p plus 1 over q plus 1 over r. So if you want that essentially this has any chance of happening, this equality, well, then chi has to be positive. If chi is negative, it probably will never happen. On the other hand, it's more sophisticated, but you can, Bjorn explained this to me yesterday at the restaurant, you can interpret chi, in fact, as some sort of Euler characteristic of, what you call that, an orbifold?
Orbifold or stacked.
Or a stacked, yeah, well, I don't know these things. But anyway, some of you do. It doesn't matter, let's just call it chi. And it has a completely different behavior according to the sign of chi. So if chi is positive, this is what we call the elliptic case, there is a beautiful theorem of Fritz Beukers which tells you that you have a complete solution to the super Fermat equation made up of a finite number of disjoint parameterizations in homogeneous polynomials in two variables. I didn't write it, but that's what it is. In fact, I'll show you in the next slide. So you have, given PQR satisfying chi strictly positive, you have a finite list, which you can write really explicitly. The finite being not very big, as you will see. It can be 3, 5, 7. Well, the largest will be 27. And any integer. Okay, these parameterizations, of course, parameterize, meaning that if you take any of the variable in the parameterization, which are traditionally called S and T, then, of course, it's going to satisfy the equation. But conversely, any coprime solution to the equation is given by one and only one of these parameterizations. On the other hand, I'm not saying that will be only one pair S and T. But it's only one parameterization in which it will belong. It's quite a surprising theorem. So the solution is complete and applies not only to this special super Fermat equation, but of course you can put coefficients in this equation. You can put ax to the p plus by to the q equals cz to the r. I'll just mention this one. So that's the elliptic case. I didn't write in this slide the parabolic case. I don't think I wrote it at all, because that depends on the coefficients. Essentially, the elliptic case corresponds to the genus 0 case. And the parabolic case corresponds to genus 1. And genus 1, that's an elliptic curve. And an elliptic curve, well, either it has 0 rank or it has rank greater than 0. If it has 0 rank, as it does here, then there are no solutions or just a finite number of solutions. On the other hand, if you put some other coefficients than 1, 1, 1, if you put ABC, you can have an elliptic curve with non-zero rank, and in that case, in the parabolic case, chi equals 0. You can have an infinite number of solutions. It just depends on the rank of an elliptic curve. And finally, the most interesting and deepest by far case is the case where chi is negative, the hyperbolic case. Then the theorem of Darmon-Grenville that I mentioned, using faultings, shows that there is only a finite number of solutions to this equation, given P, Q, and R. Now, I would like, let's see, what did I write on the next slide about this? I forget. Yeah, so I'll come back to this afterwards. So I would like to insist on this case. Please pardon me, I just forgot what I wrote about the... Okay, so I didn't write anything. So since I didn't write anything, I will talk. So this slide is essentially finished, but I would like to talk a little about this case, which is, of course, the most important. Only a few cases of the hyperbolic case have been really solved explicitly. And one knows they correspond either you do it using geometry, you can reduce these cases to finding rational points on curves of genus G for most of them. which is not, of course, very easy when the genus is at least 2. For 1, you can do it, usually. And there is a list, which you can find in literature, of cases which have been solved. And people like Bjorn have been working actively on this, and I think there is a student in this audience who's working on one of the harder cases. Also, you can make a computer search, and we know only 10 examples, well, up to a stupid thing. I mean, x equal 1, of course, is a stupid. One knows only 10 examples of this super Fermat equation in the case chi negative, and it's conjectured that, in fact, there shouldn't be many more, maybe 2 or 3. In fact, this follows from the ABC conjecture, because it's an excellent exercise that you can give to your high school brothers and sisters to show that if chi is negative, then chi has to be, in fact, less than or equal to minus 1 over 42. So chi cannot approach 0. It's at the largest value of negative value of chi that it can take is minus 1 over 42. And because of that, it's an easy consequence, you can show easily, that the ABC conjecture implies that there is, in fact, a finite number of solutions, even if you make the exponents vary. So the set of x, y, z, p, q, r, where chi is negative, and of course x, y, z pairwise coprime, should be absolutely finite. And as I said, we know 10 solutions, and perhaps there are 11, 12. So that's really a very interesting problem. You can also attack this problem from a completely different angle using modular methods. Again, the ribbit whiles, and all this level lowering methods. It also gives very interesting results. And okay, it's a very active area of research presently. But I'm totally incompetent to talk about it, but I wanted to insist on this because it's really very... Okay, so I'm just going to mention the elliptic case, which has to do directly with what I'm talking about, factoring over number fields. So in fact, the elliptic case corresponds only to, it's very easy to see that, that it's in one-to-one correspondence with finite subgroups of PSL2C. Now, finite subgroups of PSL2C are well known. They're the cyclic groups, the dihedral groups, and then the groups associated to the Platonic solids. So it's in fact, well, the cyclic group doesn't enter here. It's PQR equal, well, if you order them, 2 to R, where R is greater or equal to 2. So that's called the dihedral case. And then the triples corresponding to the tetrahedron, the octahedron, and the well, okay, you can read, icosahedron. Of course, you have dualities between Platonic solids. That's why you only have 3 instead of 5. And this corresponds, in fact, to the group A4, A5, and A4, S4, and A5. Anyway, so that's the triples, 2, 3, 3, 2, 3, 4, and 2, 3, 5. If you don't know this whole theory, you should learn it. It's really beautiful. I mean, theory of subgroups of PSL2C and the fact that it's A4, S4, A5, and so on. Now, there are 2 totally different methods to treat the elliptic case. The first, so that's why I'm mentioning it, of course, in this section, is factoring. So over a suitable number field, and the number field is never very large. Now, the proofs are rather tedious, of course, and they're detailed in the notes. In the dihedral case, it's completely trivial because you factor x squared plus y squared equals e to the r. You just factor that, and x plus iy times x minus iy. And if you have a minus sign, then you factor just as x minus y times x plus y. If you have things like slightly more complicated cases like the 2-4-3 equation and not 2-3-4, then you just factor x squared plus y to the 4 equals z cubed as x plus y squared I times x minus y squared I. And again, you say, well, you have a product of 2 factors. They're essentially co-prime, so each one is a cube. So for instance, in that specific case, it's an exercise, which is slightly tedious, to show that for the 2-4-3 equation, you have exactly 4 disjoint, homogeneous, 2-variable parameterization of the coprime solutions. So as I already mentioned, the existence of these parameterization is not so surprising. What I find slightly more surprising is the fact that they're disjoint, in the sense that any coprime solution is represented by single parameterization. So just for the fun of it, let me show you. I'll show you the 4 parameterization. So I need 2 slides because they're big. They're not the biggest by far. I mean, if I took some other elliptic equation, you could get parameterization which filled the whole, well, not a slide. I mean, it would need several slides just for a given single one. So here are parameterizations. So I repeat, it's the 2-4-3 equation. So you have x squared plus y to the 4 equals z to the 3. I hope the degrees match. Let's see the first parameterization. X has degree, homogeneous degree 4, 8, 10, 12. So 12 times 2 should be 24. Then y has degree 6. So 6 times 4 is 24. And z has degree 8. 8 times 3 is 24. Works out. Okay, so at least the degree is correct. But then you have to work out that x squared plus y to the 4th is equal to z cubed. Now, of course, I didn't. Is there a question? I didn't tell you how you obtain this, but it didn't come out of the blue. It just comes out of factoring over a suitable number field, which here is z of I. I mean, it's really very simple. And then you have to distinguish cases, whether 2 divides something, 3 divides something, and so on. I mean, it's tedious, but you can do it. The second parameterization is this one. Be careful of the conditions. S not congruent to T mod 2, 3 don't. It's only conditions at 2 and 3 which occur. And here are the 2 other parameterizations. I told you there were 4. And you see the last one is a little more complicated to write. Okay, whatever. You can do it. Well, I mean, anybody can do it. So what's very interesting is that, in fact, this factoring method works in all cases of the elliptic superferma equation, except in the icosahedral case 2, 3, 5. How can you factor in x squared plus y to the 3, y cubed equals z5? Because 2, 3, and 5 are pairwise coprime. So where do you factor? I mean, x squared plus y cubed cannot be factored, or x squared minus z5 cannot be factored. In the other cases, we were lucky, in fact. In fact, it's a good thing that this icosahedral case exists, because it shows that the approach that we use for the other elliptic cases was in fact not the correct approach. Well, of course, it did give the result, but it's not the right way to look at it. And the right way to look at it is, in fact, due to Felix Klein. It's a completely different method, which is much prettier, although it's also tedious, but still it's much prettier. So it's essentially was essentially invented in this context by Felix Klein, but it was reinterpreted in modern terms by Grothendieck and Bailey. And Grothendieck coined the word dessin d'enfant. Well, what's a dessin d'enfant? It's a covering. It's simply a covering of the projective line minus 3 points. And you can associate to this what's called a Bailey map. And this Bailey map has some quite amazing properties. In particular, with theorems of Weil and Bailey, you can show that this is true if and only if the map is defined over a number field, which is quite an amazing thing, since we're just talking about P1 of C. There's no number theory here. But that's not only the point. The point is that there is an algorithm which enables you really to compute the Bailey map completely explicitly, and it's very, very nice. And what this algorithm gives you in an algorithmic manner is complex polynomials, P, Q, and R, complex. A priori, their coefficients are not in number fields, but of course, the main point is that you can tweak them so they do have coefficients in number field, such that, well, for instance, if you treat the 2, 3, 5 equations, but this, of course, works also in the other cases, P squared plus Q cubed equal R to the 5. You see, that's quite a challenge. I mean, okay, I told you the solution, but try simply to write down polynomials such that P squared plus Q cubed equal R to the 5, forgetting everything I've said. Well, if you just try it with indeterminate coefficients, you may you may, as the preceding speaker said, you may wait a few months with your computer algebra system. On the other hand, using the Bailey algorithm, finding these PQRs can be done in a few seconds. So it's really very, very neat. And I repeat, you can do this in all the elliptic cases, so in the 235 case, but also in the 234 case, or in the 233 case, or the 22R case. It's a completely general method. And it doesn't use factoring. It's just a fact of algebraic geometry. It's very, very pretty. And what, as I said, what is absolutely essential is that you can choose these polynomials with coefficients in a number field. And on the other hand, by the way, did I say? No, I repeated it. They are polynomials which are homogeneous polynomials in two variables. So since they're homogeneous polynomials in two variables, they're forms. And in forms in two variables, you can act by PSL2C. So you can get, of course, as many polynomials as you want. And if instead of taking just a PSL2C action, if you take a PSL2 of Q bar action, then, of course, there still will be coefficients with coefficients in the number field. And then you will have to classify the PSL2 Q bar action. So you'll have to introduce some sort of reduction theory to find some canonical representatives modulo the PSL2 Q bar action. And you will find that there is only a finite number, a class number if you want, of such representatives. And these exactly correspond to each parametrization. It's really a beautiful theory. I mean, for those of you who are more interested in, who want to learn slightly more on dessin d'enfant, of course, there are many, many books about this, starting with the Grothendieck Festschrift, I guess, where there is a paper of Shamat, I think, and Voivodsky. But there are many, many, many papers. On the other hand, some papers that you can read on dessin d'enfant are so abstract that you don't understand a word. If you want to see my point of view, which is completely concrete and forgets all algebraic geometry, just go to my webpage. About 10 years ago, or 12 years ago, I explained to the psi.math Usenet group how you could compute the Bailey map algorithmically. It's really fun. At that time, I still read psi.math, of course. I don't even know if it still exists. So this was a program which was initiated by Fritz Beukers. And in the 235 case, it was a little painful. So as usual, when a professor has something painful to do, he asks his student. And his student, Johnny Edwards, did the work and took his PhD on this. I was in the jury. It was very interesting. And Edwards found that there was 27 disjoint parameterizations in the 235 case, at least if you identify two parameterizations which differ only by sign, because of course you can change x. In the 235 case, you can change x into minus x. If you don't identify, then instead of 27, I think you get 51. Well, whatever. Anyway, he found them all, and you can write them all explicitly. I don't think I wrote them. If some of you are interested, I can give you the list of parameterizations. It's quite impressive. But in fact, we don't care, after all, what they are. What's really interesting here is the method of solution. And of course, if you apply this to the other elliptic cases, then you recover the equations that we obtained, the parameterizations that we obtained using facts. Yes?
So the parameterizations have coefficients not over Q, is that right?
Oh, no, it's always over Q. Yeah,
But the polynomials themselves have...
you see?
Yeah, for that case, sure.
No, for all cases.
But I mean, the polynomials that you say have coefficients in a number field when you compute the Bailey map, right?
Yeah. So since you want... No, you're perfectly right. You get coefficients over a number field with the Bailey map. But since here we want to solve the 235 or other equations over Q, then indeed you have to apply PSL2C. As I said, everything comes from applying PSL2C to a basic Klein solution. And then you, of course, have to take a specific element of PSL2C, which sends the polynomials not only to polynomials with coefficients in Q bar, but with coefficients in Q. Indeed, that's absolutely true. If you do it randomly, you're not going to land in Q. But then there is only one way of doing it, and that's why there are these side conditions such that S is odd and 3 does not divide S. And so.
Does this method explain the disjointness of the parameterization?
Yeah, because it's exactly the notion of class. It's because it's a class number, a class. You have classes modulo the action of PSL2C, and these classes are disjoint. So each number falls into a given class, so can correspond only to a given parameterization. I think it does exactly like that. Okay.
There's the orbit, and there's finitely many orbits.
Yeah, exactly. There are finitely many orbits. So now, thank you for these questions. Please keep going, because in fact this is a place of my talk where I will stop, and I have to change. I have to change my computer. So please.
Actually, would you mind explaining, or I don't know how much time it takes, explaining a little bit how the Bailey map is used?
How you compute the Bailey map?
No, how you use the Bailey map to construct these parameterizations. That part I didn't take.
Oh well, how you use? That's what I said. Wait, maybe I wasn't clear. The Bailey map gives you automatically P, Q, and R.
Bailey map applied to what curve?
Okay, well then I guess I would have to draw something on the blackboard.
No, it is trouble.
No, it's explained on my webpage, but it's okay. Well, well maybe I'll do this at the end. It's really really you're right. It's really something fun. I would prefer going on, but please. Okay, this is a very interesting question. In fact, I can discuss it either at the end or in the afternoon or this evening. I can show you how to do it. So, I mean, when I discovered this 10 or 15 years ago, I really spent months playing with Bailey maps. I mean, there is no abstract theory there. It's just fun. Other questions? Okay, so please wait 1 minute and I get all this. What I see on my computer screen is not what you see here, so it's not that easy. Okay, so now I go to the last topic of my talks. I'm not absolutely sure, I say this to the organizer, I'm not absolutely sure that it will be able to fill completely the five talks which were allotted to me. But okay, I'll see. Is this a problem? Probably more like 4.5. Okay, so I assume that most of you know elliptic curves, but still, okay, I'm sorry I did this with number fields. I will do it again with elliptic curves very rapidly. I would like to recall what you need to know about elliptic curves. So a very important set of Diophantine equations is the search for rational points, or sometimes integral points, on curves. So you classify curves by their genus, which is closely related to the degree, and the most important examples, I guess, are if you take a non-singular plane curve of degree d, then it has genus d-1, d-2/2. So this gives 0 for lines and conics, 1 for plane cubics, 3 for plane quartics. So you see you don't have any genus 2 in there. On the other hand, a hyperelliptic curve is a curve of the form y² = f of x, where f is a polynomial of degree d, where f has no multiple roots. Now, if d equals 3, well, let's say if g equals 0, 1, 2, and 3, this curve is non-singular, so you get the same formula, you get the same things. But if d is greater or equal to 4, this curve is singular at infinity. So you cannot apply the general formula. And the general formula is given here. It's simply the integer part of d-1/2. So this gives 0 for d equal 1 and 2, genus 1 for degree 3 and 4, genus 2 for degree 5 and 6, and so on. So if we want a genus 2 curve, the standard way, well, that's a theorem which follows from the Riemann-Roch theorem, that in fact a genus 2 curve is always hyperelliptic. It's unfortunately not true in higher genus. So in fact, you can always represent a genus 2 curve as a plane curve y squared equal f of x, where f is degree 5 or 6. So an elliptic curve is simply over some field k, is a curve of genus 1, but where you have to add the condition that it has a rational point over k. So elliptic curves are important for many reasons, essentially because genus 0 and genus greater or equal to 2 are things which are, well, okay, curves of genus 0 are very well understood. Essentially everything is algorithmic. Maybe I'm pushing my luck here, but I guess everything is algorithmic. It's not that trivial, this statement, but you can say that everything is algorithmic. On curves of genus greater or equal to 2, very little is known. I mean, of course, people spend their lives on curves of genus greater or equal to 2. That's because it's exactly because it's difficult. So there are lots and lots of things you can do with it. But still, it's very difficult. And also, so genus 1, elliptic curves have a very rich structure and so many important theorems and conjectures about them, which make them really one of the most beautiful things you can study, beautiful kinds of curves that you can study. So, of course, the main reason why they're rich is that it has a natural group law. So I remind you what you need to know. You can give an elliptic curve by equations, and the simplest is a simple Weierstrass equation with no term on the left, y squared equal a cubic. More generally, you write y squared plus a1xy plus a3y equal a cubic. And of course, you have to add the condition that the curve is non-singular. More generally, you can give an elliptic curve as a non-singular plane cubic with a rational point, of course, or by hyperelliptic quartic, but you have to be careful that the leading coefficient be a square. Otherwise, there's no reason to have a rational point. You can also give it as an intersection of two quadratics, and so on and so on. Okay. Now, there are algorithms to transform all of these forms into a Weierstrass form, so it's natural to assume that our equation is given by a Weierstrass equation. So the set of projective points of an elliptic curve given in Weierstrass equation is very simple. It's simply the affine points plus a single point. There is a single non-affine point, which is the point of infinity 0, 1, 0. And this set of points form an abelian group under the secant and tangent method of Fermat, which, of course, everybody knows. If you take P and Q distinct point on the curves, you draw the line joining P and Q. I'm sorry, I didn't draw the canonical drawing of this because I don't know how to do this in tech. So you take 2 points on the curve, you draw the line, it intersects in a third point, and that's not, of course, the sum. In fact, P plus Q plus R is equal to 0. So you take as sum P plus Q the symmetrical point of R with respect to the x-axis. And if P equals Q, you do the same, but using the tangent instead of the secant. Just a little warning. If the equation of the elliptic curve is a plane cubic, that's what you do. I mean, I said this for a Weierstrass equation. More generally, if it's a plane cubic, you do exactly the same. But if, for instance, if it's a hyperelliptic quartic, this is not the construction you have to use. You don't intersect with lines. It's very simple to explain what you have to do, but be aware that this simple construction only works for cubics. Okay, now what happens when you take specific base fields? Well, when the base field is the complex numbers, then in a canonical way, the set of complex points of your elliptic curve is in bijection with the quotient of C by a lattice lambda, which is a two-dimensional Z module, discrete Z module in C. And this lattice has periods, a basis, and this basis can be computed from the elliptic curve very simply. It's called the periods of the elliptic curve. course, the basis is not unique, but you can, two bases differ only by SL2Z. And you have a map from the complex numbers to the elliptic curves, which is given by the Weierstrass P function and its derivative. This, at least in France, is taught in every undergraduate course in complex analysis. It's one of the most beautiful illustrations of Liouville's theorem, because you define the Weierstrass P function by essentially saying that it's an elliptic function, a doubly periodic function, and Liouville's theorem immediately tells you that the P function satisfies a differential equation, an algebraic differential equation, P prime squared equals 4P cubed minus G2P minus G3. Okay, all this is very standard. So we know what E of C is. It's C over lambda. Another important case is the case of finite fields. That's important to cryptographers, because now it's recognized that it's really very important to do elliptic curve cryptography, because RSA has become really very fragile. People like Dan Bernstein are killing the possibility of using RSA, because you can factor, well, not yet, but it'll come, 1024-bit numbers or more. So anyway, so elliptic curve cryptography in particular is important, but anyway, even in mathematics, it's really very useful. So you have the Hasse-bound, which tells you that the number of points of an elliptic curve over a finite field is very close to q plus 1. E of fq minus q plus 1 is less than or equal to 2 square root q. It's not that easy to prove. It's not very difficult, but it's not totally trivial. When K is the p-adic field, QP, or a finite extension, we have a very good understanding of E of QP. Well, I mentioned three names, so please correct me. It's maybe that I need to put other names than these three, but okay. These three certainly did things on that. So we have rather a good understanding of E of QP. Now, there is, of course, one field which is the field closest to my heart, which is K equal Q, or more generally, a number field. And of course, this is the most interesting case for number theory. It's not at all interesting for cryptography, but that I don't care. And in the case K equals Q, you have lots of theorems, and probably the most important theorem, basic theorem, of course, as we go along, I'll mention also the Bircham-Swinton-Dyer conjecture. The major theorem is the theorem of Mordell, which was generalized by Weil to number fields and abelian varieties, which states that if you take an elliptic curve over a number field, well, Mordell was over Q, then the group of points of this elliptic curve is a finitely generated abelian group, called the Mordell group over K. What does this mean? This means that E of K can be split into the torsion subgroup, E of K subtorse, which is a finite group, finite abelian group, and a group, a free group, something isomorphic to Z to the R. R is called the rank of the curve over K, the algebraic rank. And it's very easy to compute algorithmically the torsion subgroup. There are many, many ways to do this, starting with the Nagel-Lutz theorem, but in fact the Nagel-Lutz theorem is not so much a very nice method for computing it. There are many much better methods for this, but at least it's effective. And also, there are only a finite number of possibilities for this torsion subgroup, but this is much deeper. One knows this finite number for a few number fields. One knows it for the first result was obtained by Maser, who showed that there were exactly 15 possibilities for K equal Q. Then was work of many people, Kamieni, Kenku, and so on, and it culminated with the work of Merel, who proved that there was only a finite number of possibilities and giving bounds for any number of fields. And I think the list is completely known for quadratic fields and certain cubic fields. I'm not really an expert on this. Anyway, so as I mentioned in boldface at the end of this slide, one of the major unsolved problems on elliptic curves, of course, is to compute algorithmically the rank, and together with a system of generators. This is totally, one doesn't know how to do this, and if we could, it would really be a major advance in computational number theory. So the goal of the rest of my course is to explain methods to compute the Mordell-Weil group over Q, simply, E of Q, either rigorously or heuristically. Now, heuristically, let me elaborate on this word. Heuristically can mean two things. Either it can mean that, well, we use some conjectures. Well, that's not very important to use some conjecture. After all, we want a result. So we use some conjectures, and at the end, we obtain a result. Now, the result may depend on the validity of the conjecture, in which case, of course, we're only partially happy. But still, it gives some information. But also, there are cases, as you will see, where we do use conjectures, but at the end, the result that we obtain did not depend on the fact that the conjecture was true or false. You can just check that your result is correct. So your result is checkable. But sometimes the result is not checkable. In that case, well, if the conjecture is false, your result may be false. So the heuristic word, the word heuristically here, can mean two different things. You have to be quite careful about this. So, as I mentioned, there is no general algorithms, only partial algorithms, which luckily can work in most cases, and some people here are world specialists on this. So, to give examples of such techniques, the simplest technique, certainly, which was invented very long ago, is called two-descent, with or without a rational two-torsion point. Maybe now is the time to explain what descent means. Well, essentially, descent means that if you take some curve, maybe it has a rational point on it with coefficients having 10 digits. Well, descending this curve means that you give another curve or a set of other curves where the coefficients of the points on these other curves, instead of having 10 digits, well, they have, for instance, 5 digits. So it's much easier to find points having 5 digits than points having 10 digits. That's descent. For instance, in the work of Bjorn and other people on the 2-3-7 equation, on the 2-3-7 equation, I think one knows how many solutions are known? 5, 4?
16. Well, if you include the 1, 0.
Oh, if you, yeah, okay. Well, anyway, there's a finite number of known solutions for the 2-3-7 equation. And in the 2-3-7 equation, these solutions, some of these solutions really are rather large. I mean, some coefficients have, I don't remember, 10 digits or 12 digits. And in fact, in the covering techniques that are used by these people, I think the final points that they obtain after descents, coverings, and all this are, what is it, plus or minus 1, plus or minus 2, things like this. It's really very impressive descent. Okay. It's not exactly descent, what they're doing, but similar. Okay, so that's two descent. That's what the word descent means. Okay. 3 descent is the same thing, except that you do it for the prime 3 instead of the prime 2, and it works particularly well when you have a rational torsion subgroup of order 3. Well, of course, in general, you can do it also in general, but then it becomes hard because you have to work in number fields which start to be a little large. And there are people like Kathy, for instance, here, who work on a project involving doing general descent for NEP. It's really hard. The theory is not absolutely complete, and the practice is probably much further away than complete because it's going to involve computing in number fields. Well, okay. Anyway. Another method is to use L functions. This will be my last slide for today. Another method is to use L functions to compute the rank, only the rank, but not generators, not the generator. Now, that's a very nice method because that one is the heuristic, one of the heuristics methods I mentioned, where the result is not guaranteed. The result depends on the truth of a conjecture. But it's really very nice because it's really very simple. You just, okay, there is an object which we call the L function of an elliptic curve. I'll describe more precisely what that is next time. And you just compute the order of its 0 at s equal 1. Very simple. You compute L v1, L prime of v1, L double prime of v1, and you go on. This can be done in an algorithmic way. There are excellent algorithms, at least if your elliptic curve is of reasonable size. And you just go on. as long as it's 0, and as soon as it's not 0, you hit, well, you've computed the order at s equal 1. And the conjecture of Burchett, Swinnerton, Dyer, one of the parts of this conjecture, is that this is exactly going to be the rank. Now, there is a slight problem in this, quote, algorithm. The first problem is that, of course, it uses BSD. Well, that's okay. Why not? I mean, I don't mind using conjectures. But there is a much more serious problem, which I think I already mentioned, is that, okay, you compute L of 1 and you find that it's 0. Probably you can prove it. L prime of 1 is 0. Probably you can prove it. But L double prime equals 0? I don't believe you can prove it. I think nobody knows how to prove that L double prime equals 0 when the sign of the functional equation of the elliptic curve is equal to plus 1. Of course, when it's equal to minus 1, L double prime of 1 is 0. But when it's equal to plus 1, L double prime of 0, you can compute algorithmically very fast. In less than a second, you find that there is 1,000 decimals equal to 0. Sure, okay. So that doesn't prove it's 0. On the other hand, to prove that a number is non-zero, I'm sorry, I'm repeating something I said last time, but to prove that a number is non-zero, that's algorithmic. Okay, so that's a very nice method, because really it will tell you, if you really want to know the rank of your elliptic curve, there is no problem. You do this and you have the rank. Unfortunately, of course, it doesn't give you the generators, but at least you're convinced what the rank is. And the final method, which is what I gave as a student project, which is really one of the beautiful algorithms on this subject, is the Heidner point method. And the Heidner point method is really one of the most amazing aspects of the whole theory. It's important both in theory and in practice. It's important in theory because it's thanks to the Heidner point method that the Burchett-Swinnerton-Dyer conjecture was proved, at least for rank 1 curves. Well, combined with lots of other things, of course. And another aspect which is really appealing is that elliptic curves, you can classify them as rank 0 curves, rank 1 curves, and curves of rank greater or equal to 2. And most experts now agree on the fact that rank greater or equal to 2 curves form a proportion of 0. Mark Watkins would tell you that it's probably x to the 19 over 24 plus epsilon, up to x. So it's probably negligible amount. So you have curves of rank 0. Well, you have no problems in curves of rank 0. You don't have points to find. It's just torsion. So all the curves you have to study are just rank 1. And Heidner gives you the answer. Thank you for your attention.